Newton's Raphson method of approximating roots is what we are going to cover in this lesson. We have seen how to use iterative formula when you get xc, then you subtract off, and then you get a tolerance, and so on. Now, this one is a bit better method because it converges faster than the other method of using the iterations. Okay, so now we are going to drive it using the graphical method because we have seen how do you approximate a root using the graphical method. We say when you have a function, another function where they meet, there will be a root. So there will be an approximation. So this one we are doing it, I think remember in the previous lesson that when these two meet, this and this when they meet here, now this one is going to be our initial approximation always. So now, so this curve here, f of x, is touching here. Now this one is going to be the exact root of that equation because we say when it touches the x-axis or y equal to 0, that's the solution to that function f of x. Now, you see that this line here is a gradient to this to this curve here. So it's that for it, it's going to be following that curve. It's that it's going to be, when it touches this, it's going to be closer to this value we are looking for. But we say because this is approximation, the values just rose. Now, you start from x and the initial approximation. You start this one is far from this exact root, but this one is closer. So meaning, as you move closer to xn plus 1, xn plus 2, you are tending more to the root. Meaning that now, this one is going to be a better approximation than this because this one is closer to the root. This is our initial approximation. The line AB is a tangent, so here what we are going to use the gradient method. Using the graph shows that xn is the first approximation of the root of f of x. As we said, when they meet, that one becomes our first root. Now, not point A, this point A here is xn plus 1, the y coordinate is 0. Then point P, this one is xn, fxn, because they're telling us that this is x, and then this is the y value. So now, if I get the gradient of AP, it will be the same as the gradient of AB. Now, getting this, we say this is a change in y over change in x. So it's that our change in y, we get now this minus this, then this minus this. That's what we have. When you simplify this, we get to that. But also note that we said in calculus of differentiation that the gradient of a curve and the gradient of a line at a point is the same. So you start this line is meeting this line, this curve is meeting this line at this point. So meaning the gradient of this curve and that of this line are the same at the point P. So now from there, we say that the gradient of f of x, we say that we get a gradient of a function, we check that function, but not at P. Now here's our x value is going to be xn. So when we get its derivative, now if we substitute the x value at this point P, that's what we get when we substitute where this x, we put xn at this point. So we say the gradient of the line FP and the gradient of this curve at this point are going to be the same. We have seen the gradient of the curve is this from here because we said to get a gradient of any function, it's as good as differentiating and substituting in the x, the y value at that point, but this function only had x, that's why you substitute in there. So now, it means that the gradient of this line is going to be the same as the gradient of this. So you create it and we cross multiply this times this, we get it to this side, and then 1 times this, we get this. Open the brackets, this times this, we get xn, this times this, we get that. Now, bringing this side, and taking this side, it becomes a negative. So a positive to a negative, then this one is negative, it becomes a positive. Now we want to know this beta root always, the one next to the root. This one always next to the exact root. We want to make it the subject. So I divide this by this, by this, by this. Instead this will cancel. So I made with xn plus 1 equal to xn over the function of xn, putting in that root, then the derivative of that function, and this is what we call the Newton's Raphson formula for approximating roots of equations. And you also know that xn plus 1 is always a better approximation to find the root of f of x than xn. Why? Because from here you can see that this one is closer to the root than this. So when you move more and closer to this, then the next xn plus 1 is always going to be a better root. Now members, all you need to know that this function is the function over its derivative. I think you can see this function over its derivative when you are substituting in the initial root. Now in the next lesson we are going to see more examples. Don't forget to subscribe to the channel. See you in the next lesson.